Let's see required moment of inertia according to UG 29. So if you open the code book, the code given two moment of inertias. So the first one is for only for finding moment of inertia for only stiffener ring. This is only for stiffener ring only. So and there is one more formula which is combined stiffener ring plus shell, guys. Shell. Stiffener ring plus shell. So why code given these two formulas? So if we calculate moment of inertia for first one and second one, you will get more moment of inertia to second one, right? So more moment of inertia means more strength. So here you are getting more moment of inertia. Why? Because you are in denominator you have 10.9 and here you are 14. So obviously you will get higher moment of inertia here only. So why the code given 10.9 for this formula means here you are considering shell also a stiffener ring, guys. So because the shell also taking some load, right? So only stiffener ring not taking all the load. So shell also taking here load. So that's why you are getting high moment of inertia, high stiffness, high strength in this case. So I hope you are understanding. So that's why code given different formulas for stiffener ring and stiffener ring plus shell combinations. So generally we consider stiffener ring only. So if you calculate stiffener ring moment of inertia for this first case and you are not satisfying the requirements, so then you need to increase the shell dimension, stiffener ring dimensions, right? So in that case your weight of the vessel also increases. So in that scenario you have your option that you need to use stiffener ring plus shell to calculate the moment of inertia. So I hope you understand this point, guys. So if you found moment of inertia only for stiffener ring, it will give high thickness for stiffener ring, guys. So to withstand the external pressure. But here shell also withstanding some pressure, right? So that's why second formula also given in the code by changing the denominator values only. Okay, this means that the required moment of inertia will be higher for shell section if you include in it in the available moment of inertia. I is equal to available moment of inertia. In the previous slide, we calculated, right? So that is available moment of inertia. And the I dash is the required moment of inertia of a stiffener ring cross section. And the I dash S is the required moment of inertia for combined ring and shell cross section, guys. And then AS means cross sectional area of the stiffener ring. So only for stiffener ring. Okay. So LE, what is LE? LE means width of the shell. So how much width we need to consider while calculating required moment of inertia of combined ring and shell cross section. So if you go to code, the code given one formula to find out the width of the shell. So this much length only you need to consider. This much value only you need to consider. That is 1.1 into root of d naught into t, guys. So this much length only you need to consider to calculate the moment of inertia for your shell and stiffener ring. I hope you understand. So next one is LS1. So what is LS1? So one half of the distance from the center line of the stiffener ring to next line of support. So I will tell you clearly. So if you are placing the stiffener ring at the middle of the shell, right? So it will, for example, your stiffener ring only consider 100 inches. So up to 100 inches only the stiffener ring will withstand the load. So 100 inches means, for example, here to here 100 inches. Okay. So so up to here only, the load which are acting up to this distance only, the stiffener ring will take that load only. So whatever the load acting here and here, so it will not take that load. Okay. So LS1 equal to half of the L1. L1 is the line of support length. So here, firstly, we have line of support up to here. Correct? L. So by adding the stiffener ring, your unsupported length is divided into two parts. This is L1 and L2. So you need to find out LS1 here. So LS1 is equal to half of the L1 plus half of the L2. So here half of the L1 plus half of the L2. If you have stored stiffener ring, so you need to consider L3, right? So LS2 is equal to LS2 is equal to half of the L2 plus half of the L3, guys. So this is like you need to calculate LS2. This is the safe distance between the stiffener rings, guys. This length decides at what distance you need to place your stiffener rings and how many stiffener rings generally you require. Okay, I hope you understand. So next one is A. So you need to find A. So if I already told you this is factor A, guys, which is determined from figure G in ASME BPVC section 2 part D subpart 3. If you go there, you will find CS charts, HA charts, So in the charts, you will find figure here by using B value. So I hope up to here clear. So whatever the available momenta we calculated in the previous slide must be greater than required moment of inertia. So then only our design is safe. I hope you are getting my point. P is the external design pressure, and D naught is the outside diameter of the cylindrical shell cores or tube, and T is the thickness of the what shell. So whatever the available moment of inertia of a circumferential stiffener ring shall be not less than the determined by these two formulas. So previously we calculated one available moment of inertia for a stiffener ring, right? So that will be greater than these two values. Then only our design is safe. Okay. So these are the sample diagrams given in the code. So for your reference only, I have placed it here. So this is at least the line of support, guys. So at least the line of support. Line of support means what? It is the imaginary line on which vessel rests or it's supported. So line of supported means it is the distance from h by 3 from the shell and head combination to the this one. Okay, so this h by 3 distance also acts as a stiffener ring. I already in the previous lecture I already told you all these points. So in vessels without stiffener rings, the alloys is located at the h by 3 distance from the descent of the vessel. So if there is a stiffener ring, it is the distance between the center of the stiffener ring to center of the second stiffener ring. So LS1 I already told you it is the safe distance between two stiff rings of a vessel. Okay, so this is the LS1 formula I already explained in the previous slide. So all the variables we find out except factor here, right? So let's find out factor here, guys. So we know that we already assumed the D naught, LS, and all other stuff. So if you go to code, the code given to find out B value, guys. So this is the formula to find out B value. First, we need to find B value to find A value, guys. So by using this formula, we will find the B value. Then we will find factor A value by using the factor B value. If you go to ASME section 2, part D, subsection C, you will find CS2 charts and HA1 chart. So so these two are related to ferrous materials. So according to your material, if you use carbon steel for your material or high alloy steels as a material, so according to materials, you need to choose the charts, guys. So if you select one chart, so you already know factor B value and E value, Young's modulus for your E value. This is the Young's modulus lines. So if you draw a horizontal line and if you draw a vertical line, you will get factor A value. So for example, this is A value 0.00078. So this is the generated graph, guys. So for original graph, please refer ASME BPVC section 2 part D subsection C. So if your B value falling above these values or you are falling in this region, so at that time the code given a is equal to 2b by 3, so direct formula is given to find out the factor a value. So where e is the Young's modulus, guys. So you have a question that how do I find out Young's modulus for my material if I don't know, right? So if you don't know a for your value, so the code given one chart, that is tm1 chart in section 2 part D. So if you go there, so for different materials, different compositions, and for different temperatures, you have different values for your modulus of elasticity for your material. So this is how you need to find out E and B values, A values. After finding this A value, you directly submit it in the IS. Okay. So this is how you need to calculate required moment of inertia for your stiffener ring according to the code. So whatever the after finding this required moment of inertia, you need to compare it with available moment of inertia. If available moment of inertia is greater than required moment of inertia, then only stiffener ring is adequate, then only our design is safe. So you need to remember. So otherwise we need to choose different cross section or we need to increase dimensions of that stiffener ring to satisfy our design criteria. So this is all about UG29, guys. So I hope I added some value to your time. So if you understand my lecture, please share to your friends also, subscribe my channel and hit the like button. Thank you, Jai Hind.